Dear students, welcome to Sia's digital classes. Today's concept is central limit theorem. Let us check it out. What is central limit theorem? CLT we can call. So central limit theorem is this theorem states that the distribution of sum of IID, remembered IID, identically independently distributed. Like from sem 1 we are learning this. So whenever our distributions are independently distributed, we'll write IID, right? So here also sum of identically independent distributed distributions will consider. So random variables will be normal asymptotically under general conditions with mean mu is equal to summation mu I and standard deviation sigma, where sigma square is equal to summation sigma 1 square. So these are the conditions, nothing but we have a distribution which is identically independent, as well as we have a it is normal distribution taken from with a mean mu as summation mu I and variance as sigma square is equal to summation sigma square, sigma I square. Okay, so central limit theorem, these are the conditions. So next, what is the formula for that? Let us check it out. So whenever we have that mean and variances, we get a distribution as Sn is equal to x1 plus x2 plus so on up to xn, that is Sn is equal to xi. So Sn is equal to xi will be the formula for us, and for the random variables with mean mu I is equal to expectation of xi, we know that mean mu I is equal to expectation of xi will consider, as well as variance sigma 1 square is equal to variance of xi. So this is your central limit theorem considering the normal distribution identically independent random variables, and taking its formula as Sn is your central limit theorem. And we have some cases under this different type of situation, how to utilize that central limit theorem. We have some conditions. Let us have a glance on that also. So cases of central limit theorem. Following are the some cases of central limit theorem. So let us check it out. What is the first one? De Moivre's Laplace theorem, first one we have. So let us check it out. What is that? It is the first case of central limit theorem which was stated by Laplace. So Laplace is a person we have, he has given for us this entire statement. So let us check it out. What is that? According to this theorem, the distribution of random variables with respect to the probability of success P is asymptotically normal as n tends to infinity. So here binomial distribution has been involved. Whenever success probability of success P we have, it goes to infinity, then what are the conditions? Let us check it out for that. So x random variable x will be xi is equal to 1 if the probability is P, and it is 0 if the probability is Q. So the same probability conditions under binomial whatever we have, that is same here for De Moivre's Laplace theorem we have. So those are the conditions. Xi is 1 if probability of success will get. If it is a failure, I have to consider probability as 0. So those are the conditions under central limit theorem. And the central limit theorem, the same formula, Sn is equal to x1 plus x2 so on up to xn as n tends to infinity, because we are considering some normally distributed when the probability of success is P. So n tends to infinity. Infinity times n can extend it. So that is your De Moivre's Laplace theorem under case of central limit theorem. Now let us check it out one more case. So Lindenberg Levy theorem. So these are the two persons who has given for us, who has proposed these assumptions. So this theorem was proposed by Lindenberg and Levy by considering two assumptions. So these two persons, they have considered some assumptions here, so that we can utilize our central limit theorem. So what are they? Let us discuss now. The distribution of random variables is independent and identical. So again the distribution comes as identically independent only. That is your first condition. Now let us check it out for the second condition. Variance sigma square must be finite. So variance, whatever variance you are considering, that must be finite. So it can be calculated one. So finite data you have to consider for variance. So now next these two conditions we have to utilize to get this case. So let us check it out the formula how it goes on. This theorem states that under the above assumptions, if the random variables are distributed with the mean and variances again with the mean expectation of xi is mu1, you have to consider, and variance of xi sigma square. The same mean and variances of normal population, normal distribution, the same conditions we have to take under the assumptions of first two. Then so the same the sum will be the same central limit theorem condition, that is Sn is equal to x1 plus x2 plus so on up to xn, which follows normal distribution with the mean mu is equal to n mu1 and variance sigma square is equal to n sigma 1 square. So this is your second case of central limit theorem. Now let us check it out the third case. So Leoponov's central limit theorem. This is another person who has given this theorem for us. Let us check it out. What are its conditions and how it is utilized in central limit theorem. So this is a generalized case of central limit theorem where the distribution of random variables is not identical. Till now we have considered independently identical random variables. Here they specified that they are not identical. So they are not same. If the distributions we will consider, different cases will consider here. So not identical. So in this case, third absolute moment rho cube is considered whose distribution can be given as. So third moment we are considering here as rho cube is equal to summation I is equal to 110 rho I cube. So if the third moment if you consider, so in this case which are not identical, then how the conditions goes on, let us check it out. So then under general conditions, expectation of xi is equal to mu I again, variance of xi is sigma I square again. So the same mean and variances are the same. So what happens with the third moment if you want to consider? So then limit n tends to infinity goes to p by sigma, which is equal to 0. So whenever if you want to apply the limit for p by sigma, it goes to 0. So this is a condition we got in the third case. Then the sum x is equal to x1 plus x2 so on up to xn follows again normal distribution as a mean mu1 and a variance sigma square. So that's what in notations they have given, where mean mu is equal to summation mu and variance sigma square is summation I is equal to 1 and sigma I square. So all almost all the three cases comes out of normal population with the three different conditions where central limit theorem is utilized. So this is your central limit theorem concept, and under that three different cases. So hope you have understood this session of central limit theorem. See you all in the next session. Thank you.